Right. So this is a kind of memorable lecture for me, at least. Since we had the makeup week, this would have been last Friday, but still, this is the lecture where we just found out that we were going online only last semester. So I scrapped this lecture last semester, and I just talked to the class about what to expect and everything. Going online only, what I was thinking. I still didn't have everything ready because it was the day after. Like, we just found out. I think that Wednesday and then this Friday. That Friday was the day where I'm like, look, this is what I know so far. This is what my TAs know. We mostly don't know anything, and kind of just chilled with the class. So it was a memorable lecture. It's kind of eerie coming back to this one. So there wasn't really a lecture today. I'm going to do examples. I'll do live coding and examples of functional programming, trying to tie all the functional programming ideas together. So it'll be a more casual lecture. I'll try to interact with chat more, just like I did for the last lecture of the previous two learning objectives. This will be the third learning objective in a row, where the sixth lecture is examples and interacting with chat and demos. Yeah, that's right, P. I like getting more demos. I see lecture as a mix, trying to find the right balance between covering the concepts, going over examples in slides, and then doing live demos in IntelliJ. I think those are like the three attack vectors where I'm trying to educate you. And I'm maybe a little low on demos, but I don't know. Too many demos, it might be too much. I also heard from a TA that a student told them, I don't know how common this is, but that a student says whenever I switch to IntelliJ in lecture, they just shut the lecture off, which I don't understand that attitude at all, but hopefully, I guess if they understand everything and they can knock out all the homeworks and lecture questions, more power to them. But the fact that they were talking to a TA probably tells me that they don't know what they're doing and that they could benefit from watching the demos. So let's talk about this lecture question. This lecture question is designed to be fairly tough. It's still a big jump from this lecture question to genetic algorithm. But it is tougher than the other lecture questions. I wanted to make sure I bridge that gap at least a little bit to prepare you for that homework. So for this, we're going to create a class that's going to keep track of votes that are cast for different candidates or whatever. I refer to them as candidates, but thinking of the upcoming election. But whatever it may be, something that's going to count votes that you're casting. So this vote counter is going to take a list of strings in its constructor that is every vote that's been cast so far for any candidate, and a cast vote method that takes a string and adds a vote for that candidate to the list of all votes, a submit votes method that takes a string for a candidate and also the number of votes to add to that candidate, and you should add that many copies of that string to the list, and a count votes, which takes a string and returns the number of votes that have been cast for that candidate. And then a test suite, test vote counter to test all of this functionality. So for this, the key part of this, of course, this is 115 level question as is, but of course we're banning var, which makes it a 116 level. How do we do this without variables, and specifically with vote counter being an immutable object? So this class creates immutable objects. You cannot change this list of strings. I should make it clear that that's a val. But var is banned, so I guess that's implied. That you can't append to this, you can't reassign the reference to this list of strings, so you have to get this done without variables. That's the challenge that we have before us today. It's 60% lecture, 30% demos, 10% examples. If I think, well, at least in my mind, I'd swap the demos and examples. I do way more like worked out examples, like Wednesday when I have sample code and then I break it down in the slides with here's what's going on in the stack and the heap and everything. And then I do like 10% live coding is roughly my breakdown. But that would be the breakdown. So you would do more demos, fewer examples, and a lot of lecturing. Assuming lecture just means conceptual, I think I'm pretty far away from that. more examples better. And some of it's, and I'm restricted because I only have 2.5 hours a week to cover lecture content. It does limit what I can do by quite a bit. So I'm always rushing through things. I feel like I just need to free up more time and get more time in the class, which I'm actually in talks with some of my colleagues. We might be changing up some structure next semester. How do you know if you passed yesterday's interview or not? I have to process them and get them up. So it might take a little while. Unfortunately, you just got to wait. That's one thing I also want to fix. How can we get those results to you like immediately? But that's tough to do. All right, so let's go through some examples. If you download the slides, you'll see 3 examples. I have them written as lecture questions, and I'm just going to go through these and code them. Code them live so you get an idea of how you should approach problems like these. So this question, number guesser, which I actually wrote for today's lecture question, and I know most of you might not want to hear this, but I thought it was a little too easy, so I figured I'd do it as a lecture example, so I can still use that lecture question, but it was just too easy for the lecture question. And there's one thing that's a little tricky that almost makes this too hard for the lecture question, but you'll see what I mean. So let's go through this. Create a number guesser game. An object number guesser. There's my mouse. A method, guess the number, which is going to be a typical number guessing game where you guess a number and the person says higher or lower. This would be, the typical use would be somebody says, I'm thinking of a number between 1 and 100, and then you guess 50, and they say higher, and 75, lower, 62, or whatever, and do like a binary search to guess that number until you get it correct. The twist here is that we're working with doubles, not integers. So we can guess a number to, a lot of precision, a lot of decimal places. We get a function to be able to tell us the higher or lower. So that's kind of our oracle. We can ask, hey, how's this number? And then that function is going to say higher or lower, depending on whether the hidden number is higher or lower than the number we get it. So this function takes a double and returns a Boolean, true if higher and false otherwise. And our goal is to return the hidden number to 2 decimal places. Like examples over demos. Yeah, and that is why I do more examples than demos, when it's completely broken out in slides and you can revisit the slides. Plus, when I do live coding, I might forget to emphasize a certain point that's important. So I do favor the dissected examples instead of live coding. But I do like to mix in some live coding too. Processing grades, that would be a good question. Doing some stuff with grades. All right, so let's build this thing. And again, just like last time, I have the question over here on this screen. When I'm looking over here, I'm referring to the question text. So in a package named functions, which I set up a little bit of this, I know you can't see this part, but I'm creating the number guesser object, number guesser as an object, and that has one method in it, def guess the number, which takes an upper bound as a double. That's the lowest possible number that we should guess, and an upper bound. Man, I wish I could type better. That's something I gotta practice. And a function, I'm gonna call it oracle. I used that terminology earlier. An oracle, which is going to take a double as a first order function, take a double and return a Boolean with the specs that I described earlier. And this is going to return a double, which is the number that I've arrived at. So this can be read as I'm thinking of a number between lower bound and upper bound, And this is us. This is the function that we can use to ask questions. How about this number higher? How about this number lower, etc. I'm just going to have this return 0.0 for now as we set up our testing. And test, just to make sure I'm consistent, test number guesser. And let's set up some tests. Let's get a little cheeky here. And we want to think of the tests that are going to get all the edge cases. So let's start with number guesser. And technically, I would change my package to tests to really get the question here. Oh, the auto import. I'm not going to do that just because I don't feel like swearing at the auto import. So if I had some number guesser that said, I'm thinking of a number between 0 and 100, to go off the example that I gave when I was reading the question, 0 and 100, and some guessing function. And I'll create that on a separate line just to extract out the first order function part of this, which is one of the big topics we wanted to focus on here. So I'll give it the same name, Oracle. This is a function that's going to take a double and return a Boolean. So the type of this value is going to be double to Boolean. I'm going to assign that just like we would do like val x int equals 7. We're going to specify the type, which is a function that takes a double and returns a Boolean, just like the type here is int. And we're going to assign that some value, which is going to be a function that takes a double and returns a Boolean. We do that in a similar way as we do when we define a method. So we're going to give it a parameter list, an input of type double, which I'm going to name input. Use the big arrow to specify that this is a function that we're declaring. Reorganize things a little bit here. So to specify that this is a function that we're declaring. And then let's say that, actually I want this to, I'm going to end up using this. Some hidden number of type double. And let's say we're thinking of the value 60. And now we want to return true if the number that we're guessing, input is the number that we're currently guessing. If that number is lower than the hidden number, we want to return true. And technically the way I wrote the question should be less than or equal, but since they're doubles, equality is kind of a loosely defined thing. So here's our function. It's going to take a double and return true if that input is less than or equal to the hidden number. So it's going to return true if our next guess should be higher than the current guess. False otherwise, so false if we somehow got exactly on the double with doubles, and false if it's less than as well. So let's give the bounds here. Actually, I'm going to get rid of my magic numbers. It's generally good practice to never have numbers that don't have any names. So I'm going to give these names. Store them in variables. To make our code more clear, this is what we call self-commenting code. We could have a comment here that says the first input is the lower bound, the second is the upper bound. It's much cleaner and more accurate to store those in variables, give them clearly meaningful names, and then type those variables in here. Someone reading this code without my description is going to be able to understand that this is the lower bound and this is the upper bound, because that's what I named my variables. Very clear. And then my oracle. We're obviously not giving the hidden number to the function because that'd be pretty easy to guess. This is going to return a double, the guessed number, and I want to assert that the guessed number, I want to assert compared doubles, that method that I just wrote before lecture started, guessed number and hidden number. Get rid of all this. And now I have to change my epsilon. So by the definition of this question, we want to make sure that the returned number from this method is within 2 decimal places. So I'm going to make sure that we're at least within 2 decimal places of the correct answer. So I'm going to change my epsilon to reflect the logic that we're testing in this question. I'm going to duplicate this a few times. I saw negative numbers as an edge case in chat. So let's make sure the hidden number is negative. Actually, let's go negative 30. And then another edge case that we should be thinking of. Let's really put our method to the test. Negative 1,000,000, positive 1,000,000. And the answer, let's say, I'm just going to mash the keyboard, and a whole bunch of decimal places. And actually, I just thought of another edge case. What if the hidden number is 0.0? What if the hidden number is exactly the upper bound? And what if the hidden number is exactly the lower bound as well? So there's some edge cases. I could spend the whole rest of the lecture just coming up with test cases here. But this will definitely get me started. This should get a lot of what's going on. And yeah, we want to build this as binary search. So we could build it without binary search, but binary search is just, we know what it is and we like it. So we're going to give another example of binary search. No mod in chat. Don't go crazy. We had to restructure some of the TA assignments. No mod today. But it's an interactive lecture, so I'll be watching chat pretty well. Is there a reason why I define that? So I defined it in both. So oracle, I need to give guess the number some oracle. I happen to name it the same in both. And we of course should have. No, I did run this. And that's why. Because I got an error. And then I define it here. So this oracle, this is going to get assigned that oracle from my test. So of course I fail all these. I should have passed the 0.0 test, actually. I expected to pass one of those. Oh, right. That's why it doesn't show up. That's why it jumps from 3 to 5 here. It doesn't show me the results for 4 because that one passed. Yeah, it didn't get it first try. Yeah, I mean, I'm always returning 0.0, but... So you're thinking of the Oracle database. Yeah, the company, not that Oracle. So this is like an Oracle that you can ask questions and it always gives the correct response. It's something we use in security. Often if we have an Oracle, we assume that we have oracles that can do certain really powerful things and then write proofs about our security and our entropy and things like that, based on the existence of such an oracle and access to such an oracle. So that's why that popped into my brain to call it an oracle. So let's start writing this thing. So I want to say if I hit some base case return, I'm going to save the base case for later, just because we want to think about that a little bit. If we're not in our base case, I want to know if I should guess higher or lower. Actually, let me put this all in else, just the way I want to organize it. So since we're going to embrace binary search, I want to compute the midpoint between these two values. And I'm going to take a guess right in the middle of the lower bound and upper bound. I'm going to take a guess right in the middle and say, okay, higher or lower. Depending on whether that answer is higher or lower, I'm going to make my decision on what to guess next. So lower bound plus upper bound over 2.0. That's going to be my midpoint, and that's what I'm going to guess. So I'm going to guess. I'm going to say, hey, Oracle, this is a function, so I can call it. I'm going to say, hey, Oracle, here's my guess, this midpoint value. And I'm going to say, if that's true, so if this Oracle returns true, that means the hidden number is higher than my current guess. So you guessed it. I'm going to recurse on the first half. So if the Oracle says higher, I know anything between the lower bound and midpoint can't possibly be the hidden number. So my new lower bound is going to be the midpoint, and my upper bound remains the same. My Oracle remains the same. And I'm going to recurse with my new guess with the updated midpoint, so then my next midpoint is going to be halfway after that. So like if the bounds are 0 to 100, I'm going to guess 50. And then if it says higher, I'm going to guess between 50 and 100 and guess 75, and then do my binary search from there. Else, it must be lower. So the lower bound stays the same, the upper bound is gone, the Oracle is the same. And we're going to keep narrowing down our search. But when do we stop? When do we hit our base case? And how do we do it in a way that we make sure each of these calls is always getting closer to the base case? I'll let you think about that for a second while I catch up on chat. What's today's lecture question? You can go to the slides and download it. I'm not going back to it right now. Oh yeah, if you don't see it, hit refresh. I posted the slides like an hour before lecture today. Yeah, forgot to refresh. Oh. Okay. Anybody want to chat about base cases? Just about lecture questions? So our goal of this question is we need to return the hidden number with at least 2 decimal points of accuracy. Do we have a neat trick to bypass type checking? What are you referring to? When the lower and upper bound are the same. So we could do... and you know what? This might not even be the worst thing. Let's actually try this. So these are doubles. So for those to be equal, they have to be equal, even disregarding truncation errors and the like. Let's try this and see what we're gonna get. And I'm gonna try today. So usually I give these examples and I run my tests and it's just right. I'm gonna try to actually break things. I promise I'm doing this on purpose. But I'm going to try to break things so I can run the debugger, because I want to highlight the debugger today as well. It's a very powerful tool. I don't highlight it enough, and it's something that can save you hours and hours and hours of time. So we're going to say if lower bound equals upper bound, we can return one of them. If they're the same, it doesn't matter which one I return, but we've narrowed our search down quite a while. So let's go back to our tests, run our tests. Do we have a hash map in Skylight? Yeah. The regular map defaults to hash map, I believe. And it's possible that we're going infinite. for those of you really paying attention, we're pretty clearly going infinite here. With recursion, why am I not getting a stack overflow error? Let's stop that. And what we really want to do here is do our doubles checks, math.abs of the subtraction of the two. Actually, I don't even need to do this because upper bound is always going to be higher than lower bound. So I'm going to say if upper bound minus lower bound less than epsilon, which is a different epsilon than the other one. And I'm going to create this as a state variable in the number guesser object as a constant. And 0.01. Since they're not exactly the same, I'm going to do my averaging and say once lower and upper bound are close enough to each other, whatever would have been my next guess, that's going to be my answer. And I said I'd break it to run the debugger. I broke it and then didn't run the debugger. But let's run the debugger anyway and watch what's happening when we call this thing. So let's run these tests in debug mode, and we can catch a glimpse of what this thing is doing. So here's our first test case. Our lower bound is 0. I'm thinking of a number between 0 and 100. And our oracle is some function, which in the debugger we can see the hidden number, but this oracle is some function that's going to take a double and return a Boolean. So let's step through this. We're going to compute our midpoint. That's going to be 50 with 0 and 100. And we're going to ask our oracle. We're going to call this function, and we're going to say, hey, oracle, should my next guess be higher or lower? So as the hidden number here is 60, it should say higher. We're going to call this function. It's going to return higher. We could, and if you're using the debugger and you want to see more of what's going on, we could store this in a variable. Let's actually do that. You can always create more variables. Break it up, and then the debugger is going to show you more results. So let's actually restart this with that result being captured, just so we can see what's going on. Tail recursion, juicy, you got it. So we calculate the midpoint. We ask our oracle, hey, what should we guess with this input of 50? That does create a stack frame for this function call. We get our result, store it in a variable, and now we can see oracle result is true. The oracle said higher, effectively based on our example here. So we're going to say guess the number of midpoint upper bound oracle. That's going to make a recursive call with the lower bound of 50 and 100. We're going to guess 75. The oracle is going to return false. Hey, you need to guess lower. So we go to this next oracle, this next call. And we're going to keep doing that until we hit this base case. And notice our input, our upper bound and lower bound are always getting closer to each other no matter what recursive call we make. They're always getting closer to each other. So we're always getting closer to this base case of the difference between the upper and lower bound being less than 2 decimal point precision. But notice that we're not putting extra frames on the stack. We can. This is why we didn't hit the infinite recursion there. So if we did this a little bit differently, I guess answer. So if I store this in a variable or a value instead, and again for your labs, I'll make sure that I do something like this, just to make sure that I'm not testing you on tail recursion. But if I store these in values, and now I'm going to run the debugger again, we get to see more of what we would expect from a recursive algorithm like this. So now, let's just get to some point in the middle of this thing. Now, each call we make, we're adding more frames on the stack. We can see all our stack frames here. Our initial call with bounds 0 and 100. Our next call with bounds 50 and 100. Our next call with bounds 50 and 75. 50 and 62.5. And we can see all these frames being added to the stack now, because the recursive call is no longer the last thing that our method is doing. So we are going to see all the stack frames as you would expect from class. And then we can see, okay, this stack frame asks the question of this. It's sitting on this line and saying, once you return, that's going to be my answer. Once we get to the bottom of the recursion, let me set another breakpoint at our base case. So here's a debug tip. I'm going to set up, whenever your code hits a breakpoint, it's going to stop and show you all the values. So I'm going to set a breakpoint at my base case, and then I'm going to hit this button, this resume button, which is going to run the program until it hits another breakpoint. It's just going to keep running the program again until it hits the breakpoint. Now it stopped again, and I can see that I'm 15 stack frames deep. I'm 15 layers deep in the recursion before I got to 2 decimal point precision. The difference between these two values is less than 0.01. So I hit the bottom of my recursion. I'm going to return the average of those two up to the next stack frame. So now I'm going to get that answer, store it in a value, get this answer, return it to the next stack frame, return that, return it, return, return, return. And all these stack frames that are sitting on the stack waiting for those answers are going to keep returning this answer, which is roughly 60 to like 2 decimal places. 3 we happen to get. And so even this call, 50 and 75, is returning the answer to that recursive call. So as this gets returned up the recursion, up all these stack frames, we're seeing that answer that was returned and generated from the base case only, but now it's being returned all the way up the recursion. And this is what tail recursion does. Instead of passing this value from stack frame to stack frame to stack frame to stack frame, it just says, look, since all these intermittent stack frames aren't doing anything, they're just returning the value, let's cut them all out of there and just flatten this down to a single stack frame. That's what tail recursion does for you. But now if we so worth mentioning, just because you're all in computer science, negative 1,000,000 to 1,000,000, the power of binary search and the power of exponents and logarithms, the range of negative 1,000,000 to 1,000,000, when the hidden number is something that's not going to be guessed easily, it's not like 0.0 or 500,000 or something like that, still took 29 steps, 29 recursions to get within 2 decimal places of that number. It logarithmic, it works incredibly fast. It's so powerful to have a log n algorithm instead of an O of n algorithm. Extremely fast, extremely quick. It can get down there. So we weren't even worried about overflowing the stack. At 29 frames, we're not concerned about that yet. But if we do modify this, if we go back to what we had before, but without our tail recursion, let's run this, and we should see our stack overflow error. Stack overflow. Stack overflow error. What's up, Retro Gamer? So, any questions about that one? Or what we did there? I'll put up the code again, actually. I'll let you stare at the code. Infinite RAM. Yeah, and that's especially with genetic algorithm, I do expect to see a lot of veils. You can do it with, possibly 0 veils, but I would expect most of you are going to have a lot of veils in the code. Actually, I'm going to skip to the third example next, just because I'm thinking about that now. If they're equal, epsilon would be redundant. If they're equal, they would be equal out to the precision of a double, which we're not always going to get to. The way doubles truncate, it's not going to happen. But we could add a few more zeros here and get more accuracy. Actually, let's run that in the debugger. So even to get this kind of accuracy, 35 depth of the recursion, 36, 49. This should be the this is the million to negative a million to a million, and you want to guess this number out to some ridiculous precision. 49 recursions. That's the power of logarithms when you have log n runtime. Crazy fast. Crazy fast. All right. So I actually want to number guesser. I'll sideline this one because I want to jump to this just because I mentioned the other thing, the doing things without veils. So for this one, in your vote counter class, add a method named winner, which returns the candidate with the most votes. So this would require having everything with the vote counter done. Of course, I'm not going to give you the answer to the lecture question. Definitely moved the wrong video feed there. But I'll set up a little bit of this. It's a class named vote counter, which takes votes a list of string and returns the string that occurs the most in this list, effectively. Whoever has the most votes. And we're going to assume that there's no ties. This is a good practice, too. I was on the edge of adding this to the lecture question, but it's just a little bit too much, I thought. So I left it out. And we also have, as part of your lecture question, this count votes method, which takes a string and returns the number of votes for that person. I'm just going to always return 10 because I'm not going to give away the answer. Winner is written as winner. Maybe that's how I spell winner. Full count named winner. Yeah, that's... Whoops. There, I'm consistent at least. So we want to return the candidate with the most votes in this list of votes. And I'll do this quickly. I won't set up tests and everything because I do want to get to the other one. This is kind of a... If I got to it, it'd be nice, but I decided to do it earlier. So votes... taking the list of all votes. So you can think about how you would do this. I would be interested to see all the kind of different solutions here. But I'm going to call distinct, which we saw in the anagrams example. This is going to remove all duplicates from the list. Actually, do I want to do it like that? Yeah, I do. So that's going to give me a list of all of the candidates. And then I'm going to pull out my old sorting methods. I'm going to do sort by and give it a function that it's going to sort by. In this case, actually a method, which is the count votes method. No parentheses because I'm not calling it. I'm just giving sort by the count votes method and sorting the candidates by their numbers of votes. reverse that list so the winner's on top, and return the first element in that list. We can actually cut this down a little bit. We don't actually need that. That just cuts down the amount of work that the method does. But this is, I don't know, I thought it was a little bit too much for a lecture question, but this is what you could get at. This is a very succinct way to be able to represent that. We could also do sort with count votes underscore negative. Can I not do that? Well, I'm not going to go down that path because it's going to be boring to watch me debug that. But we could actually remove this. And I kind of want to get one more out of there. But with functional programming, you'll see, especially during your genetic algorithm, you can do a whole lot without a whole lot of code. So think of how you would do this without functional programming, the amount of stuff you would end up doing, the amount of loops that you would have, and all kinds of extra code. This, you can be way more expressive. I want to take the votes. I want to get all of the unique candidates out of that, sort them by their number of votes, reverse it, and take the first one. So take the highest votes. Done. And you can chain methods. I do have a bonus slide for today as well. The chaining methods like that. Since these lists are immutable, and each time we call a method, we're returning a new list, we could take this and assign that a new list. So this is what I mean by you can have a lot of vals, but you don't have to. I could be like new list equals that. New list dot sort by that. Val newer list equals, I can break this into a whole bunch of lines and call these one at a time. But since this returns a list, saying new list dot sort by is the same as putting sort by right here. That's doing the same thing because this resolves to a list, and I can call methods right on that list without storing it in intermediate variables. And since I'm returning that new list that I create right away, I don't have to have any vals here. And you can do this in genetic algorithm. That's a bit more of a stretch because there's a lot going on there. But you can, you could do these assignments without any vals either. Technically, this isn't needed either. So I wouldn't see any educational purpose to it, but I could ban val as well. You could do these things, I believe, without any vals. Depends on the specific question. Try if you do genetic algorithm without vals, I would be interested in that. For the next lecture question, the next lecture question is going to be linked lists. So that'd be, I don't know, maybe possible. You'd have to write an immutable linked list though. We're going to do mutable lists in lecture. So that'd be tougher, but possible. You don't need variables at all. If you really embrace functional programming, you don't need variables ever. Okay, so let's do exponentiation. I want to raise a double to the power of an int. For full credit, this should run in n log n time, or not n log n, log n time. Oh, where am I? There I am. This one I set up a little bit here. I want to kind of rush this a little bit just because I want to get some code, which is something every programmer has done. Once you start rushing, all good practices just go out the window. Def exponentiate, I think I called it something like that. I created a Java class for some reason. I must have clicked the wrong button on the interface. Let's rename this so it's not Java. And this is going to take a double and an int, and raise a and return a to the power b. Turn a to the b. Okay, that's gonna bug me with that warning. As a double. So there's a simple way. I'm just gonna call it pow because I don't know how to spell that. So there's a few simple ways to do this. I guess we would do math.pow a comma b, and we could just be done, I guess. That's not how we're going to do it, obviously, because we want to actually do some things. We actually want to see how code works, which is why this doesn't make a good lecture question either, because so many people just try to call math.pow. Numbers.pow. Let's get some edge cases first. This should be 1.0. Compared doubles. Can't do equal here. And I need an extra set of friends. So 1 to the 100 should be 1. 20 to the 0 should be 1. 2 to the 1 should be 2. 2 to the 10 should be 1024, right? And let's take advantage of doubles at some point. 3.35 to the 5. I'm going to cheat a little bit on that and use math.pow to generate my test case. And let's do something like -3 to the 3 should be -27. Make sure we get some test case like that. And we're going to assume that we're not supposed to handle negative exponents. So let's run this and make sure math.pow works and get the answer to our test case here. Actually, how I would normally do this. I don't like using code like that to test code. So what I would do is use my handy dandy calculator. 3.35. 3.35 raised to the 5. Should be this. Oh my goodness, it didn't copy. 4219140959375. I should be able to pass that test with math.pow. So our test passed, but we cheated. So let's actually implement exponentiation. And I'm kind of just really quick curious. It's not going to give us the definition. Okay. So one way we can do this is the slow way. Let's do an O of n way first. Let's say if we're in the base case of b, we're going to say if anything is raised to the 0 power, return 1. Else, return pow of a to the b minus 1 times a. So this is the easy way. This is the, the standard. This is what we would use to show you recursion kind of way. There's a big problem with this, though, which we won't really... Oh, wait, no, I did set this up so we can see it. Is if I add another test case here, and I say... Let's do 1.01, I'll say. Let me go to my calculator and get the answer here. Raised to the 50,000. Let's do, no, let's leave it like that. And that's 1.1713566 E216. Let's copy this, undo our code here, run the test to make sure we have the right thing. We passed that test. Let's paste our code back in. Run this test. So we know we got the correct answer because we tested it with our calculator and our math.pow. And somehow that passed. Okay, that's impressive. Let's set our breakpoint. Oh, we're 5 minutes over already. Jeez. Because I'm running the old test. I changed the test name, and now it's not running that. So I got to recheck the math.pow. Since I changed the test name, this button up here wasn't working anymore because it was running the wrong test. Print line debugging. One 713. You know, I probably just didn't have enough precision. Especially since I'm checking this, which is, you know, not even close to the amount of precision that I have here. I think that's going to get us into trouble. I'm not going to bother. Because we can still get the point here. We can still get the idea. Is that this is going to overflow our stack. TC116 never ends. This is going to overflow our stack because, of course, we're putting 50,000 stack frames on the stack. We're not going to be able to get that much. So we got to rethink our solution if we want this to be very versatile. Math.pow obviously gets over this hurdle. So let's also get over this hurdle. So what I want to do is be a little bit smarter about what I'm doing and get this down to the log-n algorithm. Obviously, that's a linear runtime algorithm in terms of B. It's O of B. So let's get this down a little bit and then get to 442. 442, if any of you are showing up early, it is just an activity. It's all posted. So I don't really have much to talk to you about right now anyway. If this does go a little bit more over. So let's think about what we're doing here and think of B as its binary representation, kind of hitting on what we did last time when I was converting binary to decimal. I'm going to check if the least significant bit is a 0 or a 1. If the least significant bit is a 0 or B is even, if B is even, then A to the B is the same as pow A to the B over 2 squared. So I'm going to store this in a variable, or a value rather. I want to square it, but if I used math.pow, it's kind of defeating the purpose of writing my own pow method. And return result times result. If B is even, I want to do the same thing, except I have an extra factor of A that I need to add. So if B is odd, I'm going to compute this. 1/2 of B, I'm going to square that. That's going to be A to the B minus 1. Since this is odd, this was integer division. So I need to add in that plus 1 again. Get at that last one. When I run this, we'll see if we get precisioned out. Maybe this exactly computes it. So I'm getting truncation errored here. The precision is just going to be a little bit off. But we do get, you can tell we get the same value. And let's run this in the debugger. And instead of 50,000 stack frames on the stack, which one was this? 1 to 100, yeah. I was wondering why there were so many frames for that one. 1 to 100 again. Oh, yeah, I gotta resume. 2 to the 0. Just hit the base case. 2 to the 10. Took 5 recursive steps. And let's get to the good one. So when I called this with 1.01 to the 50,000, it only took 17 stack frames, 17 recursive calls to get down there. To get to that base case, which is 1.101 to the 0. That returned the base case of 1. We got 1 from this. We're going to square it and multiply it by A. Oh, I got to step through this. It's going to square it and multiply it by A. A was 1.01, so we're going to return. Oh, we can't really see the. No, we can see result. I lost what I'm looking at. Oh, there. I wasn't looking at the right result. But it's going to keep recursing. It's going to keep returning up the recursion and squaring that value. And if you keep repeatedly squaring, even just 16 times, the numbers get ridiculously huge. Very, very fast. So I can't quite use equal doubles because I'm testing to this precision, but that precision is at least 216 decimal places or 216 positions away from the precision that I'm actually representing. So I would need to set my epsilon to something like 10 times 2 to the 110 to be able to get an accurate equals double check using the method that we've been using. And obviously that large of an epsilon is going to make sure that all of these always pass because it's super duper generous. So I would have to rearrange my equals double method to use like a percentage of the value. As long as they're within 1% of each other, allow that. So I'd have another thing like, or like, let's try this. Well, you know what, I'm not gonna, because even if it passes all the tests, it might just be because I coded this wrong and allowed way too much variance. But I am using the equals double method, but it's just not set up to handle enormous numbers like this, times 10 to the 216. It's just not ready to handle that. Yeah, and the double takes, it's a 64-bit value, and then a certain number of those bits are used for the mantis, which is the decimal portion, and a certain number of bits are used for the exponent, and then 1 bit for the sign. So I would want to check only the precision of the mantis is the way I would want it set up, but I'm not doing that right now. Not happening right now. And we got through the 3 examples. I mean, I had to go a little overtime there, but Not too bad. Hey, your tower server isn't firing because it's taking too long. 65 milliseconds for single value. I mean, it should take the same amount of time for a single value, or, you know, no matter how many dimensions you have, it should take the same amount of time if you don't change your parameters. But it depends on the specifics of how it's set up too. It depends on what your base case is. Are you taking a lot longer to reach your base case if you're in higher dimensions? But really, this is exactly why I give you the line testing. You should test with line, and if you can get lines really fast, you're going to be able to get the tower server and the aimbot really fast. If you skipped over line, you shouldn't be talking to me about anything. Do the testing that I gave you. It's there to help you. It's there to make your life easier and save you time. Please take advantage of it. Okay, there's nothing more frustrating than a student who's like, I'm having trouble and I've spent 40 hours on this assignment. I'm like, oh, did you do the thing that I gave you to help you do this and not spend 40 hours? No. Why are you even talking to me? You've already ignored my advice. You're going to ignore my later advice too. Why bother me with that? Take my advice. Like, I'm here to help you. One bit for the E? Oh, well, the E is just how it's represented as a string. So the E is implied. That's not part of the 64 bits that it needs to represent that. That's just when it's printed to the screen, its toString method adds that E in there. I wonder if we could actually see that. Apparently not. It's going to be hidden somewhere. Fun fact, since I was scrolling by it, all these methods that we call, these are actually methods. I'll show you one cool thing before we switch to 442. So, like, if I wanted to add two numbers, like 3 plus 4, we would normally do it that way. But we can actually call the plus as a method like this. It's just a method named plus. There's nothing special about it. You can, in any method that only takes one parameter, you can actually write an infix notation like this. Let's see, did we end up writing any today? Like count votes takes one parameter. So I can actually write that infix like this. That's a perfectly valid way to call the count votes method. This is exactly identical to this. It does the same exact thing. Any method that takes one parameter, you can write an infix notation like this. So there's nothing special about when we use infix notation for like plus or modulo. Or equal. These are all just methods, but we're taking advantage of Scala's infix notation to write them in a way that's, you know, a little more pleasing to our eyes. But we can call all these as methods. So I'm calling the method named slash, which is our division. It's a neat little tidbit of Scala. So there are no actual... Oh, man. So there are no actual operators in Scala. Like some languages have these defined as special operators. Scala says, nah, they're just methods. Call them as methods, but will let you write any method that takes one parameter in infix notation. Let me find another example, because you can get some really weird looking things. Polynomials. Oh, I never gave any sample code for polynomials, though. Here's one. Like first n primes is a method that only takes one parameter. Oh, yeah, that's just like the one I already gave. Yeah, it's just like that's the same syntax. I was trying to find a different one. Where do let me go to objects. This will be the last thing I say. I gotta switch over. I mean classes. I need a class example. Item is more expensive. Item main. So I can do cereal is more expensive milk. So this is a method that takes only one parameter. So I could call it using infix notation. Or the standard notation. This is how we're used to seeing that. But with Scala, we can use this infix notation just like we do with addition, multiplication, etc. That we like to see an infix notation, so we write it in infix notation. We can do that with any method that only takes one parameter. And if you prefer that, it reads more like a sentence, if you like that. But just a neat little Scala thing. It's not really critical to the course, but if you're wondering, how Scala works, there's a neat little thing of how Scala works.